So as I was saying, internal energy of a system is the sum of internal kinetic energy and potential energy processed by the molecules of that system. Okay, so which means internal energy equals to internal kinetic energy plus internal potential energy. So the diagram, so indicator diagram is just a graphical representation of change in state of a system. Change in state of a system. That's what indicator diagram is. So as you can see, this is a thermodynamic system. So this is the level. This is the internal energy at the moment, right? So this is the initial. This initial diagram is telling you that this is the state of that thermodynamics before it is applied. Okay, so we have the pressure, the volume, and the internal energy. Okay, so when it is applied, the change in Q, delta Q, when it is applied, the volume changed, right? It's increased. The internal energy also increased, right? And then the pressure, there is a shift from here to here. Okay, so you can see the distance of the change in the change made on the matter. So you can see change in height. So which means from there we can denote that the total work done by this thermodynamic system, the total work done is equals to force multiplied by height, right? So the force, the amount of heat you put, right, multiplied by displacement, how much the system was displaced while applying your heat. Okay, so if we put that as equation 1, okay, then from the equation you can see pressure there. Pressure means the force you applied on something per unit area. If this is an area, so if a pressure is applied on all of the area, so I'm applying a kind of pressure per unit area. Okay, and if it is this point alone I want to apply, so per that area, so the amount of force I'm applying is pressure. Okay, so which means P equals F over A, right? So and from that we can make F the subject of formula, right? So because we want to represent our F there with pressure instead, so F can be equals to P, pressure times area, right? So PA. So we now substitute the value of F now for F in equation 1. So and from there we are going to get what? Changing the amount of work done now equals to P A ish, right? And area itself and height, area of something multiplied by the height will give us the volume, right? Volume of that. So you can again say pressure multiplied by change in volume. Okay, so from there you can get when you say something is changing something, you can also rewrite it as pressure multiplied by the new volume minus the initial volume. So P multiplied by V2 minus V1. So that's how we arrive at the formula for thermodynamics. Okay, so for first law of thermodynamics, when heat energy is converted into other form of energy, or other forms of energy are converted into heat energy, the total energy in the system before and after conversion remains the same. So this is a special form of conservation of energy. What I just telling you is that amount of heat energy you put and the amount of change it has brought to the system, they remain the same. Okay. If each supply to the system is changing Q, it is equals to increase in internal energy of the system, right? Plus the work done by the system. That's what the first law of thermodynamics is just telling you. So change in amount of heat that you apply to something we lead to change in internal energy of that system, and also we there plus the amount of work done by the system. That work done is the change that it was made due to the heat. Okay, so change in internal energy plus the work done. So when do we know all these things are positive or negative? So the amount of heat that you apply, the change in Q will be positive when it is supplied to the system. So this is when you supply heat that it will be positive now. So and when and the heat will be negative on that system when it is taken away or it is withdrawn from the system. Okay.